Good morning, guys. See, the other day we discussed about the zero order kinetics. Today we'll discuss about the first order kinetics and important formulas and important graphs which are usually asked in exams. Let's see that. So when it comes to first order kinetics, if any reactant A is giving products, we typically write first order kinetics as A naught to AT, which is the concentration, and the change in A is associated with K into A raised to power of 1. And this on integrating, we get concentration of A is equal to A naught E raised to power of minus K into T. Okay. Or if I write in terms of time, that can be written as ln 2 by K of the reaction, ln 2 and K of the reaction into uh, log of, sorry, 1 by K. 1 by K of the reaction, ln A naught by AT. Okay, this is another way of writing it. So these are different ways how you represent the first order kinetics. See, AT can also be written as A naught minus X. Okay, and if you write that in terms of A naught minus X, so here we'll be writing it as A naught minus X is equal to A naught e raised to power of minus KT, and X will be equal to A naught into 1 minus e raised to power of minus KT. This is another way of representing. X is called the extent of the reaction. X is the extent of the reaction. AT is the concentration of reactant at a time t. So either you represent in this way. This is most frequently used once while solving. This is the part we should be using the most. Got it? Now, going into further details into it, you know how to write the half-life. So T50 or T half will be when AT is equal to A naught by 2. So when AT is equal to A naught by 2, then T will become ln 2 by K of the reaction. Got it? Which comes out to be 0.693 divided by K of the reaction. Okay. Suppose if it is given T75 or T 3 by 4. Got it? So that implies when AT is equal to A naught minus 3 by 4 times of A naught has been consumed, which makes it is 1 by 4 left. Correct. So in that case, T75 will be equal to ln 4 by K of the reaction or 2 times of T50. So which gives you an idea that every time you start going 50% of all of that, so you would notice that you will have, integer value, integral value of T50. Okay. If you have it for lastly, T is equal to T of 1 by n. Okay. Then AT has to be A naught minus A naught by n, which makes it n minus 1 by n of A naught. So T 1 by n will be equal to ln n by uh, n minus 1 by K of the reaction. Okay. So this will be the formula for T 1 by n. Got it? There is another term which we need to define here. What is an average? Okay. Average uh, average time, average life. Average life, T average, right? It is basically defined as integral 0 to infinity Ct dt by C naught. That is how the concentration is changing over the lifetime with respect to the initial concentration. Correct? So if we substitute the values like 0 to infinity, Ct can be written as C naught e raised to power of minus kt into dt divided by c naught. So if we work out on that, we will get t average life is equal to 1 by k of the reaction, correct? And 1 by k, we know that we can write in terms of half-life as T50 by ln2, T50 by ln2. So which means T average is approximately 1.44 times of T50. Again, important formula that could be asked, while solving questions. Right? So more or less, if you notice the formula based from first order kinetics, these are the things which you need to know. How to represent T, time, how to represent the extent of the reaction, how to represent the T half, how to represent T1 by N, and finally average time. Okay. Now, graphs wise, if you compare, we'll see that first graph, how AT is changing with respect to time. So this is how it is changing. Next, if you write in terms of, T half, you write in terms of T half, how it is changing. T half will remain constant with respect to time. Clear? And any time factor, correct? If you notice that T 1 by N, that will also remain constant like this as time goes on. Clear? If you notice extent of reaction, X versus time, that is progressively increasing this. Got it? These are the types of graphs you would be asked, what would happen to the concentration or time, in various cases. You got to also see that suppose if T is equal to 0, initial concentration is A naught. And if T is equal to T1, concentration is AT, which is equal to A naught e raised to power of minus K into T. And if time T equal to 2T, then AT will be equal to simply A naught e raised to power of minus 2KT. And if time T equal to 3T, it will be AT is equal to A naught e raised to power of minus 3 KT and so on. So you can see there is a geometrical progression which has been observed. It is a GP series is been observed here, having a common ratio of e raised to power of minus Ka into T. Correct? So this would be an application that could be asked. You'll be created a scenario where time is increasing uh, in a periodic way. For that periodic time increase, how is the A changing? Okay. You're supposed to find out a relation. Maybe if it is an infinite series, you know how you can figure out on the sum. Okay. Now, what are the applications of first law? The first application is about decomposition decomposition of H2O2, right? H2O2 using KMNO4 titration or in titrations. So if you use KMNO4 and titrate with H2O2, correct? Now, depending upon whether you have a freshly prepared H2O2 or are we taking some time after that. So H2O2 generally decompose as a first order kinetics into H2O and half of O2. Clear? So if at time t equal to 0, if this is A naught and this is nothing, and at time t equal to t, it got decomposed to this amount, A naught minus x by. These are in terms of number of moles you take or concentration you take. Yeah. Then how much amount of volume that is required? See, at this current time when the titration is been done, when you make a freshly prepared H2O2 and then you make a titration to convert into Mn plus 2 and O2 in acidic medium. Okay. Then for this particular amount of number of moles, then let's say, sorry, if this is the number of moles, the volume that is required by the volume that is required by fixed concentration of KMnO4, let that be V naught. Okay, this will be V naught concentration into some normality N, and this is A naught. Okay, and if you notice at at this time, so Vt into N is the equivalence of KMnO4, while this is AT, which is equal to A naught minus X. Okay, so if you compare the ratio of these two, it should be same only, correct? Because the number of equivalents required by KMnO4 and the number of, the number of equivalents of H2O2 and KMnO4 should be equal. And assuming that these are equivalents or moles, that multiply that with the valency factor 2, that will still get cancelled anyway. So that's why if you compare the first order kinetics, so you can directly write down K of the reaction is equal to 1 by T into ln, what is the concentration of H2O2 initial by H2O2 at time t. Okay. So this can be related with respect to the volume that we have consumed. So ln, we can write this as V naught by Vt. So V naught being the volume used in the freshly prepared H2O2, and Vt is the volume used uh, after time t for the same peroxide. This is the first application, guys. Second application is based on second application is based on the decomposition of the first order via first order of different cases, which we write in terms of pressure. So suppose A is given to decompose as 2B gas plus C gas, and this is A gas. Okay. See, most of these decompositions follow first order kinetics. So wherever you see this kind of cases, you can always assume it to be first order. And now suppose I have to derive K of the reaction in terms of T, P naught and Pt, where Pt is being the total pressure after time T. Correct. So if we have to write it this way, A giving 2B plus C, T is equal to T naught. This is P naught initially at time T equal to T. So this will be P naught minus X, 2X and X, which makes this P total value as P naught plus 2X. Correct. So X will be equal to Pt minus P naught uh, uh, by 2. Okay. If we substitute this back into the reaction here, so I'll write K reaction is equal to 1 by T ln P naught by P naught minus X. So 1 by T into ln P naught by this P naught minus value of this one, Pt minus P naught by 2. So that will give you K reaction is equal to 1 by T ln 2 P naught by, 3 P naught minus Pt total. This is one way of representing it. Clear? You would be given questions where these values are given, okay, and at a particular time, or either you are supposed to calculate the time or calculate the rate constant depending upon the P naught and Pt given. Second case, second case is when instead of Pt, P infinity is given. Okay, something when a P infinity is given. So which means you have to derive K reaction in terms of in terms of you know P naught, sorry, Pt and P infinity. Yeah. So you see that A is giving B plus C, right? At time t equal to 0, if this is P and this is P naught, at t is equal to P naught, this is P naught minus X, X and X. Okay. See, at infinite time, you will not have any A left and everything will be converted into 2 P naught and P naught. So this total pressure is what we call it as P infinity. So P infinity is this total pressure, which is 3 P naught. And P total in this case will be equal to P naught plus 2x. P naught plus 2x. Okay. Now, what is the formula we write? K reaction is equal to 1 by T ln P naught by P naught minus x. Correct. So now this P naught need to be replaced in terms of P infinity and x need to be replaced in terms of Pt. So if I substitute these values, see, x is equal to Pt minus P naught by 2, while P naught is equal to P infinity by 3. So I hope you understood what to substitute. Okay. So if we substitute these values, you would get somewhere like 1 by T, ln 2 by 3 P infinity by P infinity minus Pt. This is what you will get. So these are very, very standard questions, guys. Please learn it. So how we can relate K of the reaction in terms of Pt and P infinity, while here P naught and Pt. Here, see, there are other cases also, but like I said, I'm touching all the important ones. But if you get an idea how to try this out, you can check out other cases as well. Okay. Next. Next one, let's see hydrolysis of sugar. Hydrolysis of sugar. Hydrolysis of sugar mainly is being done with respect to the uh, angle of rotation for sucrose, glucose, and fructose. So overall reaction is this: C12H22O11 aqueous solution plus H2O liquid will convert into C6H12O6. One is glucose, the other one is C6H12O6, which is fructose. One important part here is if there are n moles of glucose forming, there are n moles of fructose also forming. They form equal number of moles. So here, if originally if this is A naught in terms of moles at time t equal to 0 and at time t equal to t, so this will become A naught minus x and this will become x and x. Clear? And at time t equal to infinity, everything will convert into A naught and A naught here. Okay. You know that this is a dextrorotatory. This is a dextrorotatory sugar, while this is a levorotatory sugar when it comes to sucrose, glucose, and fructose. All right. So here, if you notice the rate of the reaction, rate will be equal to, K into sucrose concentration into H2O concentration. Clear? So order seems to be 2 here, but water, wherever it is used as a solvent, right, especially for hydrolysis, it will have high concentration. Concentration of water is around 1000 by 18, which means the change in the concentration of water is extremely low. So we can consider this H2O as constant, and therefore we write this as a new constant K dash into sucrose concentration power 1. So order now here is 1. So this is called pseudo first order kinetics. Pseudo first order kinetics. Correct. So all we know is that we need to put that in terms of sucrose concentration. Okay. Or either in terms of sucrose number of moles ratio or pressure ratio or anything. So here the formula typically is K reaction is equal to 1 by T ln number of moles of sucrose. Initial number of moles of sucrose is A naught, and now it is A naught minus X. Now somehow this A naught and A naught minus X, which is this two, we got to represent in terms of their rotations. Okay. So now notice this one. Initially, when only sucrose is present, when only sucrose is present, then number of moles is A naught and it is directly proportional to the rotation R naught. And this R naught possibly is because of the rotation. Rotation is only because of sucrose. Okay, angle of rotation on polarimeter is only because of sucrose. Next, we have A naught minus X, correct? So you can notice that for A naught moles, if R naught is the rotation it can make, for 1 mole, it can make R naught by A naught. So for A naught minus X moles, then it can make A naught minus X by A naught into R naught. This much is the rotation of sucrose can make. Clear? Well, after time, at infinite time, you will see the rotation is 2 A naught, and this is because of glucose and fructose together. So 2 A naught is giving R infinity. So now for 1 mole of glucose plus fructose, the rotation that happens is R infinity by 2 A naught. R infinity by 2 A naught. And at time t, what is that amount of at time t? What is the rotation we are getting? We are getting x and x. So for 2x, how much it should be? So that is R infinity by 2 A naught into 2x. So if it is for 1 mole of the mixture, if this much is the rotation, for 2x moles, how much is the rotation? This much will be the rotation. So the total rotation at time t at time t will be equal to, you know, uh, this will be a naught minus x. So for a naught minus x, I have told you that this is a naught minus x by a naught into r naught, which is swept by sucrose, and with glucose and fructose we are getting r infinity into x by a naught, and this entire thing should be proportional to rt. Okay, this much is the rotation which you are getting. Clear? So now using this, if you compare RT here, sorry, this is equal to RT. So if you compare this value here, so we will get A by A naught by A naught minus X is equal to R naught minus R infinity by RT minus R infinity. So therefore, the final formula what you will get is K reaction is equal to 1 by T ln R naught minus R infinity by RT minus R infinity. Okay. So again, a lot of you may not understand how to derive it, but end of the day, you need to know, you should be able to use these formulas properly. So if you know this formula, if R naught, R infinity and RT are given, directly substitute them, try to figure out what will happen to the K of the reaction. Clear everybody? So this is what we are supposed to do. Next. The next application of the first order kinetics, right, uh, is about hydrolysis of esters. Hydrolysis of esters. So that is example. If you notice CH3CO C2H5, right, aqueous solution plus H2O liquid. This will convert into CH3COOH liquid plus CH3CH2OH liquid. This is about hydrolysis of esters. Okay. Here, the reaction again can be written in terms of some K dash into ester concentration, which makes it pseudo first order kinetics. Pseudo first order kinetics. But remember, this reaction is most favorable in acidic medium. Okay. So, which means it depends on the concentration term. So, more the concentration, more could be the K value. So, one JE question, let us just focus on that question, how it is being asked, right? So it has been said hydrolysis of ester was carried at, a molar of HCl. In one scenario, it is a molar of HCl and a molar of H2SO4, correct? And it has been asked in which case T will be more. In which case T50 will be more, correct? So you notice this H plus concentration is A molar from HCl, and here H plus concentration is 2A molar from H2SO4. Got it? Keeping that in mind, now I can say rate constant of HCl has to be less than rate constant of H2SO4. Higher the concentration of the cat. See, if anything which is acting like a catalyst, that will always influence the K value. That we learn it in Arrhenius equation. But remember for now that as the K value, as the catalytic concentration increases, K value will always increase. So KCl will be less than that of rate constant of H2SO4. So in that case, T half, because T half is inversely proportional, T half when HCl is used will be greater than T half when H2SO4 is used. Got it? So remember that. So based on this, the questions can be framed. Okay. This question has been asked two, three times, once in mains and two times in mains and once in advance. So learn it. So just based on concentration only, you can figure out what is the ratio of the rate constants, how is the time, how is the half-life changing and all. Next, let us discuss about, parallel and series reactions. Parallel and series reactions. Okay. So if you notice the first order reactions, they can be extended towards parallel and series reactions. Parallel reaction is something where some kind of gas, let's say A is there, and it is decomposing into two different forms like B here and C here, not at a time. So both their rate constants are different. So if this is K1 and K2 here. Okay. So what are the questions which are typically asked? First question is, how does the rate law looks like? What is the rate law? Second question is, what is the ratio between B and C at any time t? Okay, at any time t. Third question is, what are the concentrations of A, B, and C at any time t? Correct. Fourth question is, fraction yield of B. Fractional yield of B. How much is B getting yield? Correct. And fifth question is, proofs of activation energy of or net activation energy. So what will be the formula for net activation energy? These are the type of questions typically asked. Okay. So first we should be able to figure out this, that any rate of change of A is reflected as the sum of rate of change of B plus rate of change of C. This is the first thing we should. And this can be written as rate of change of B is coming from A. So K1 into A, and this will be K2 into A. So in short, it is K1 plus K2 into A. And I will use this K1 plus K2 as the K overall. K overall into A. Alright, this is K overall into A. Now, if you integrate this from A naught to AT with minus dA by dt is equal to K overall into A. This is a simple first order kinetics. So we will get, you know, we will get K overall is equal to 1 by T, ln A naught by AT. Correct? This is the equation which we will get. Correct? Now notice what is the rate of B by rate of C. This is our second part. Right? First part is this, second part is this. See, rate of B will be equal to K1 into concentration of A by K2 into concentration of A. Because at any point of time, this will be the concentration, right? So these terms will get cancelled, okay? Which means rate which can be written as dV by dt divided by dC by dt. Now this dt will get cancelled. That will be equal to concentration. Sorry, that will be equal to simply ratio of K1 by K2. So which means any change in any small change in B with respect to small change in C will always be equal to constant ratio. So if we say that the change is from 0 to some concentration B of dB, that should be equal to K1 by K2 into 0 to C concentration of C, which means B by C concentration at any time t has to be always equal to K1 by K2. Again, very important while solving questions. Remember this. So the ratio of these two will always be equal to K1 by K2. Acha, K1 by K2 in this case, possibly if I change these values as 2K1 and this as 3K1, then the ratio will be accordingly. It will be 2K1 and 3K1. Okay, those type of questions we will do it. Right. Next, we know that if AT is equal to A naught e raised to power of minus K uh, K overall into T, then how much will be A naught here? See, A naught is a distribution of concentration into A in B and C. Okay. So here we got a relation between B and C already. So we can directly use that. So A naught is equal to AT is A naught into e raised to power of minus K overall into T plus B of T plus C can be now written as B of T into K2 by K1. So now you can notice that how BT can be identified from here. So you can notice that BT, if you solve it, it will come out to be K1 A naught into K1 plus K2 into 1 minus e raised to power of minus K1 plus K2 into T. This is the BT value. And if you notice CT value, that will be equal to K2 into A naught by K1 plus K2 into 1 minus e raised to power of minus K1 plus K2 into T. Got it? So the values are exactly same except here it will be K1 and here it will be K2 for BT value. Okay. Now, the next part, the fourth part is about fractional yield. Fractional yield, fractional yield of C will be simply K2 by K1 plus K2, right? For B, it will be K1 by K1 plus K2. Okay. Percentage yield. So percentage yield will be equal to simply of C will be equal to K2 by K1 plus K2 into 100 and accordingly you can check out for C, right? This will be the percentage yield, correct? So if you go back, what all things we have done, check. We got what is rate law, what is B by C ratio, what are A, B, and C values, what are the fractional values of B. And last thing is about identifying the E average. Okay. Now, activation, how do we figure out? See, we learned that K average or K overall is equal to K1 plus K2, correct? Now, K1 from Arrhenius equation can be written as A1 e raised to power of minus EA1 by RT. Similarly, K2 can be written as A2 e raised to power of minus EA2 by RT. Okay. Now, if at all I differentiate that with respect to T, correct? And overall also I can write K overall is equal to A overall A overall e raised to power of minus EA overall by RT, right? So if we take these values and differentiate them once, so we will get, A overall into e raised to power of minus E overall, E overall by RT into E overall by RT, which will come outside, that is equal to A1 e raised to power of minus EA1 by RT into E EA by EA1 by RT plus A2 e raised to power of minus EA2 by RT into EA2 by RT. This is what you'll get. So now you can notice that this is equal to K overall. This is K1. This is K2. Okay. So we got again one equation as K overall into, E overall is equal to K1 into EA1 plus K2 into EA2. So now from here I can write E overall is equal to K1 EA1 plus K2 EA2 divided by K overall. K overall is how much? K1 plus K2. So I hope now you understood how to figure out the overall uh, activation energy. So this is the overall activation energy, everybody. So please go through it once. Anyone has any doubt here, please let me know. Similarly, if you differentiate two times, you will get this equation. If you differentiate two times, E overall square will be equal to K1 EA1 square plus K2 EA2 square divided by K1 plus K2. Okay, right? See, if these same questions need to be figured out in a question like this, okay, these questions are very standard questions for both mains and advanced. Although in mains, see, this is not given much in NCRT, but they'll always ask these questions in mains. So learn it. A giving, let's say, 2B and C as the parallel equations here, parallel reactions. So here we have K1 and this is given as K2. Okay. So now while writing the rate of A, right, the first reaction would be the same thing. So we will have AT is equal to A naught e raised to power of minus K1 plus K2 into T. Here there is no change. Got it? Next. Second thing, where we had a concentration of B by C, concentration of B by concentration of C. Here you will have a change because now it is 2 times of B, which means now we will have this as 2 times of K1 into A divided by K2 into A. So that makes it 2K1 by K2. So that's how you can write. So now you know the relation between, uh, you know, B and C with respect to K1 and K2. Clear? Now, whatever that is been asked, if the percentage yield is been asked, if the percentage of B, yield of B is asked, yield of B is asked, then that will be equal to, you can take this as 2K1 divided by 2K1 plus K2 into 100. Correct? So like this, we can identify what is the percentage of B and accordingly we can calculate what is percentage of C. I have added more questions in the class notes of similar kind. Just go through them once so you get an idea uh, how to figure out the percentages in various cases. Sometimes it will be like 2A, 3B, 4 here, 5 here, 6 here. You can put all these various numbers and accordingly figure out what are the equations. Okay. Let us see about sequential reactions. Sequential reactions. Sequential reactions are when A is giving B and everything is in first order kinetics, and B is giving C. This is also K1, this is K2, this is second inverse as the units, second inverse as the units here. Got it? So at time t equal to 0, if this is A naught concentration, at time t equal to T, this is concentration AT, BT, and CT. Okay. So same way here also we can write minus dA by dt is equal to K1 into A. So from here I can get AT is equal to A naught into e raised to power of minus K1 into T. Okay. Next, dB by dt is very interesting here. So dB by dt when you write, it is gaining first from A and losing towards C, isn't it? This is what you will have. So which we could write it as dB by dt plus K2 into B is equal to K1 into A. Okay. Now, by multiplying this with an value of e raised to power of K2 into T on both sides, I would be able to solve it using, by parts, integration by parts. And that you would, from there, you would get Bt. I'm writing that value directly. Bt is equal to K1 by K2 minus K1, K1 by K2 minus K1 into A naught, and that e raised to power of K2 minus K1 into T minus 1. And sorry, minus e raised to power of minus, this will be minus 1 only. Let me write the final equation. E raised to power of minus K1 into T minus e raised to power of minus K2 into T. Okay. This is the final equation which you will get as Bt. Okay. Now, if you know Bt, you can get Ct already, because A naught will always be equal to At plus Bt plus Ct. Got it? So if you know this A naught value, At value, Bt value, we got it. So from there we get what is the Ct value also. Got it? What do we get as Ct value? Now, more than, you would be never asked questions as what is the exact derivation for Bt. You would not be asked exactly question for what is the derivation for Ct. What you would be asked is this one. Find sorry, find the find time at maximum concentration of B. Maximum concentration of B. Maximum concentration of B, as in, we will use this equation directly and differentiate this with respect to T. And if you differentiate this with respect to 2 and equate it to T 0, that is dBt by dt. If you differentiate that, equate it to 0, then we'll get an equation like this. That is ln K2 by K1 is equal to K2 minus K1 into T max. So from here, this T max is always asked to calculate. This is an important formula, guys. 1 by K1 minus K2 into ln K1 by K2. Okay. So you would remember this formula for solving questions. Okay. Now, basically what we are trying to do graphically, if you check out, so A is always decreasing. This is the concentration of A naught. Sorry, this is the concentration of A with respect to time t. This value is A naught. Similarly, B, when it comes to B, it is going at some height, and then again it is decreasing. So this is the time t max which we have just calculated. This is the time t max. This is with respect to concentration of B. And then with respect to concentration of C, if you notice, C is only progressively increasing over time. Okay. So typically you will notice that C graph would be like this. Right. So this is concentration of C with respect to time t. Okay. Now, if I club all these graphs together, there are two scenarios we can get. Okay. There are two scenarios we can get. One scenario is A is going this way, then B is becoming like this, and C is going this way. This is C. So this is concentration C, this is A, and this is B. This is one situation. So this situation arises when the K1 is extremely less than that of K2. Correct? So that means the second part is, changing very drastically. This one. B to C is happening very fast. If this reaction happens extremely fast here, that means the maximum of B comes very soon, and then it will diminish also. Okay. This is a situation. Second case is when we have Second case is when we have uh, A diminishing this way, correct? And B is forming something like this, and then C is going like this. So this is concentration C, B, and then A. So in this case, K1 has to be much greater than K2 so that we'll get sufficient concentration of B at maximum. Okay. Now this is the graphs we need to know in which case what is the uh, issue. Okay. So I hope the series and parallel reaction cases are clear, everybody. This much is what you need to learn from series and parallel reactions. Let's see another application from first order kinetics. See, it is about kinetics of bacteria and virus. Kinetics of bacteria and virus. You'll be framed with a lot of questions where there is some virus given in the body, and how does this multiply? So suppose if you have initial number of uh, virus particles as n naught, and as you take time after time t, this number of particles, whether it is virus or bacteria, right, they have reproduced and they have increased their number of organisms to nt. Then what we can write is dn by dt is equal to k into n. So again, if you integrate this, you will get ln, sorry, you will get kt is equal to ln nt by n naught. Okay. And here remember, nt is greater than n naught. Right? Nt is greater than n naught. So if just like we have T50, we write T50 as when you have half life, right? Here we write it as T double. We write it as T double, correct? So T double, which we also write it as T2, that is equal to ln2 by K. That is, whether your virus got multiplied twice, that can be written in terms of this value. All right. I hope all of you got this, how to use the cases of bacteria and virus. Simply, most of the questions you are asked is about, how much amount of time it has been taken to double, or after these many double lives, what would happen, and so on. Okay. Next application you would notice is, how we have certain adsorption on the layer. Suppose if this is an aluminum layer, and how much is the oxygen or any gas getting adsorbed on the surface. Here, suppose if this is an O2 gas which is getting adsorbed, correct? Then what is the amount of surface of the layer which we have, correct? So this surface of the layer, if you notice, this I can write it as T max, okay, or tau. This is basically tau. So tau max. Tau max is the maximum amount of distance or maximum amount of length of adsorption which can take place on metal surfaces. So in that case, we can write d tau by dt is directly proportional to t max minus t, or tau max minus tau. So we can write d tau by dt is equal to some k into tau max minus tau. So if you again, if you integrate this, you'll get kt is equal to ln tau max by tau max minus t. This this tau is a time t. Okay, this is how much is the layer that has been accumulated after time t. So this is another application. Yeah. Next application is about, equilibrium reactions. Suppose if you have A is in equilibrium with B, and this is K forward and this is K backward. If these two terms are given, then how do we write the uh, uh, time, or how do we write the K with respect to this given quantities? That is, yes, right. So at time t equal to 0, at t equal to t, this will become a naught minus x and x. And at equilibrium, see at equilibrium, the concentrations will be constant, and that let this be the change will be x eq. Now, if you derive this equation in terms of uh, in terms of k, what do we get here is k forward uh, k forward plus k backward into t will be equal to ln x eq by x eq minus x. So this is the formula that you need to remember. Again, I'm not getting into the derivation. Derivation is given in the class notes. Please go through it if you require. But most of the time questions are being directly asked here. So you would just need to use this formula, correct? K forward plus K backward into T. That will be equal to ln x q equilibrium minus x. Done? Now, check out on second order kinetics. Second order kinetics. Second order kinetics questions are not asked, only equations are asked. Okay. How does the equation look like? So A giving products, if A giving products, now if you have minus dA by dt is equal to K into A square, then you are writing the rate law for a second order. Okay. After integrating, we will get 1 by AT minus, sorry, 1 by AT minus 1 by A naught is equal to KT. So this is the equation you need to directly remember for second order. Got it? So if you notice the second order kinetics graph wise, if you check out rate versus time, it will keep increasing. And next, minus dA by dt. Now, 1 by AT versus t. If we plot this one, then I'll get a straight line here. Next, if we plot t half versus A naught concentration, this will decrease. Why, if you compare A naught here, so write down if AT is equal to uh, A naught by 2, A naught by 2, then the time is half-life, right? So T half-life is equal to 1 by K into A naught. You'll get this as 1 by K into A naught. So if concentration increases, initial concentration increases, the T half will always decrease. That will be the value for second order kinetics. Okay. Next. By chance, if the second order has to be written with two different reactants, like this, A plus B is giving products. Okay. Then initial concentration is A naught and B naught, and this will become A naught minus X and B naught minus X at time t equal to t here. And in that case, rate of reaction is equal to rate of A is equal to rate of B, which can be written as K into A raised to power of 1 and B raised to power of 1. This is as per the rate constant. Now, if I differentiate this, I'll get this as minus dx by dt, because minus dA by dt can also be written as simply dx by dt, and that is equal to K into A naught minus X into B naught minus X. So now I can integrate that with respect to X here. Okay. So what do we get? 0 to X dx, uh, 0 to X dx by A naught minus X into B naught minus X is equal to integral of K into T 0 to T. Okay. So if you are able to integrate this, so we will get an equation like 1 by B minus A and B naught minus A naught into ln A naught into B naught minus X divided by B naught into A naught minus X. And that is equal to KT. This is the equation you will get after integrating. Okay. Now imagine if B is in excess, if B naught is far greater than A naught, implies concentration of B is in excess. Just like in water, just like if you take water, if water is given, the concentration of water is high. So you can ignore A in front of B. You can ignore A in front of B. And therefore, if you check out B naught minus X, I can simply write it as B. A naught minus X, I can simply write it as B. Okay. So we can write this as 1 by, so ln A naught by A naught minus X, because this B and B will get cancelled. Here A will get cancelled. So that will be equal to B times of K into T. And B into K, I can write it as a new constant as K dash into T. So therefore, ln A naught by A naught minus X is equal to K dash into T. Can you see this is just a first order kinetics? So that pseudo first order kinetics can be derived using a general equation like this. Lastly, if you notice nth order kinetics, if you compare nth order kinetics, I'll directly write the formula here. So 1 by n minus 1 into 1 by a naught raised to power of n minus 1 by, sorry, 80. 1 by 80 raised to power of n minus 1 by a naught raised to power of n minus 1, that is equal to kt. Okay. And t half or t50 will be equal to 2 raised to power of n minus 1 by n minus 1 into a naught raised to power of n minus 1 into k, a of the reaction. Here. So if you notice this T50, it is actually directly proportional to a naught raised to power of 1 minus n. Okay. This can also be used for calculating the order of the reaction. So if T of and A naught values are given, we can actually calculate what is the order of the reaction. And in fact, that N can be derived as a formula like this, as 1 plus log of, T50 of 2 minus log of T50 of 1 as in different concentration, divided by log of a naught of 1 minus log of a naught of 2. Okay. So this will give us the order of the reaction. So I hope this part is clear, everybody. This is another way of identifying the order of the reaction. Now, guys, whatever I have written, right, whatever we have discussed, these are all quick things which we need to know as a part of this topic. All right. These are the important points from this topic. Now, coming to the next part of this kinetics is about identifying the rate constant and its relation with temperature. Okay, rate constant K versus temperature. How does it vary, and what equations are supporting? Correct. So first, it has been derived from Arrhenius equation. Arrhenius equation here, which is purely empirical. Purely empirical. Correct. What he identified is this: K is equal to A e raised to power of minus EA by RT. This is what has been identified. And if I write ln K is equal to ln A minus EA by RT. So you can see it is a equation of a straight line here when you plot it between ln K versus 1 by T. Okay, with a negative slope like this. Got it? And here is your maximum value, which is ln A. Got it? And if at all you differentiate this, I can write it as dk by dt is equal to a e raised to power of minus dA by RT into EA by RT square, if at all I differentiate this. Okay. So basically a differential form of this kind is observed. So dk by dt is equal to k into EA by RT square has been observed. This is the differential form. And if you notice, this differential form has all positive terms, correct? That makes this as positive here. Right? So if at all I differentiate it one more time, that is d square k by dt square, right? If you multiply that, I am going to get a value like this: k e a by RT cube into minus 2 plus EA by RT. EA by RT. Here. Now here we get a condition. Condition is that if I mean d square k by dt square will be greater than 0 if t is less than EA by 2r, and d square k by dt square will be less than 0, if t is greater than EA by 2r. EA by 2r, correct? Which means if you plot k versus if you plot k versus t, correct? You will see first it will go like this, a concave part, and after that it will become a convex here. So this is that point of inflection where this change is happening. And the change is happening is at EA by 2R at this particular temperature. Okay, clear guys? So keep this in mind how the graph changes when it comes to K versus T. Okay, now if you have two different temperatures, how do we plot it? How do we write the equation? ln K2 is equal to ln A minus EA by RT2, and ln K1 is equal to ln A minus EA by RT1. So if I take just the ratio ln K2 by, if I subtract both of them, ln K2 by K1 is equal to EA by R into 1 by T1 minus 1 by T2. This is what we have. Got it? Right. What are the conditions here? See, if EA increases, right, this value become more positive, which means K is increasing. And if temperature increases, this value become lesser. So again, K will increase. So therefore, as EA increases or temperature increases, K value will always rise. Okay. So this is something we need to understand. Yeah. What has been noticed is another thing which has been noticed is this one. Suppose if A is giving B in a reaction, it has an activation energy EA1 here, and this is happening at temperature 300, and as I'm rising towards 310 kelvins here, and another equation here we are having C is giving uh, some B here, but here we are getting this product with an activation energy EA2. Here also we are taking it from 300 to 310 kelvins. Yeah. Now from here I can say that ln K of 310 by 300, that should be equal to EA1 into 10 divided by R into 300 into 310, correct? Using this equation. Similarly, I can write here as ln K of 310 by K of 300. Now let me make this as for this reaction, and this is 2 for this reaction. It is equal to EA2 into 10 by R into 300 into 310. Okay, clear? Now, suppose if this value is greater than this value, if this value is greater than this value, which means EA1 is greater than EA2 because rest of the values are same only. So we can say that if EA1 is greater than EA2, then ln K of 310 by K of 300, 1 should be greater than ln K of 310 by K of 300, 2. Now, why this is important is this was asked as a graph, I think in 2018 JEE advanced question. ln K versus 1 by T. Now, there were two graphs given like this. One is a graph this way, the other one is graph this way. Okay. So, this is 1 and this is 2. So, obviously, any graph which has more slope getting more, almost as a linear form of this one, which means it has to have EA1 value greater than EA2, correct? So because here the rise of that K value is more as compared to rise of the K value here, correct? So this is the graph you need to remember. So in these two graphs, which has more activation energy? Clear everyone? Next. Check out how the temperature coefficient has been used. Temperature coefficient mu. Okay. So mu can be written as, K plus 10 divided by KT. This is the value. Okay. So we can write ln KT plus 10 by KT as EA by RT into 10 by, you know, T into T plus 10. Got it? So on as you increases temperature, you can see as temperature increases, mu value will decrease. As temperature increases, mu value will decrease. Okay. Typically, most cases, mu lies between 2 and 3. 2 less than mu and less than 3. This is the range in which it will remain. And now again write K2 is equal to K1 into mu raised to power of T2 minus T1 by 10. Right? This is something which you can use. So you can use this as a direct formula, guys. Right? So if you want to calculate the rate constant uh, after a temperature T2, right, what would happen? So you can use this. But for that, mu should be given. And most of the time, mu is being taken as 2. If nothing is given, always take it as 2. In sometimes in JEE questions, they have not mentioned the mu value, always take it as 2. Okay. Now, what are the units of K? Units of K will be same as units of A, which is mole per liter raised to power of 1 minus n and time inverse and time inverse. Got it? Because this is the general, value units for rate constant. Okay. Now there are few questions I have given based on the rate constant, based on the Arrhenius equation. Please go through them once. Last thing I wanted to discuss theoretically is collision theory. Collision theory. See, first we need to understand a chemical reaction can be a consequence of, molecular collisions. When molecular collisions happen, the energy temporarily rises up. Okay, the potential energy of all the reactants rises. It would reach to a maxima, right? Which you call it as the threshold limit or threshold energy. After that, it will convert into products. And again, the energy will come down. Okay, that's how typically the collisions work. Now, during this time of collisions, Not every collisions will be active to convert into products. Only few collisions will be converting into products. Rest of them will just make a collision and come back to the reactants. Okay. So there is a conversion rate after of all the collisions. Not every collision will convert into a product form. Keeping this in mind, you can relate the Maxwell-Boltzmann's, theory, where we were discussing about gases, right, and their collisions. Same logic can be applied here. You can see the collisions in which molecules collide, right, with sufficient amount of kinetic energy and proper orientation and a proper orientation factor that will help in breaking the bond of the reactants and making the bond of products. Correct. So what I could say that rate of reaction can be simply total number of bimolecular collisions, total number of bimolecular collisions per unit time, per unit time, per unit volume, per unit volume. Okay. That multiplied by fraction of reacting particles, which should have a good orientation. So what we can write here is this total number of bimolecular collisions is always written as Z11. In gas laws, we have learned that Z11 into fraction of particles is what you will notice as e raised to power of minus EA by RT. This is the fraction of particles you will notice. Okay. This we will get it from Boltzmann's curve and also known as Boltzmann's factor. Okay. Now, what is Z11? Z11 is equal to 1 by 2, okay, sorry, 1 by root 2 pi sigma square into U average into N by V whole square or N star whole square, correct? That into now, when it comes to concentration, so this will be equal to C, sorry, N by V whole square. Yeah, this is how much we can write. So that is equal to, I can write it as half into pi sigma square U average into, if I write this N in terms of number of moles, I can convert this into concentration term. So therefore, you can write it as Avogadro's number into concentration square. So now this C represents concentration square. Okay. So this is Z11. Okay. So now what is the rate of the reaction? Rate of the reaction will be equal to this entire thing 1 by root 2 pi sigma square U average into Na, Avogadro's number, into concentration term square into e raised to power of minus Ea by RT. Got it? Now what I could write all of this is this one and this one. If we take all of them as a one constant, I can write it as some constant K of the reaction into concentration square. Right? Obviously, if it is a bimolecular collision, if two particles are colliding with each other and that it is like an elementary reaction which is converting directly to products, then I can say that it is a second order kinetics. So that's why it is order is 2 and K reaction can be written, and this is like a rate law expression now. So we can get this as a rate law expression, which we could write it as, K reaction now can be written as, half 1 by root 2 into pi sigma square. U average, I could write it as 8 RT by pi m into Na, isn't it? Which means I'm getting a constant here, but also there is a temperature term. Rest all are constants. So I'll write this constant as A dash into root 2. A dash into root 2. And this is K of the equation into e raised to power of minus Ea by RT. Correct? Have you noticed that this is the new equation for rate constant as per collisions theory? So rate constant K is equal to A dash A dash into root 2 into e raised to power of minus EA by RT. A dash is a factor which is independent of temperature. But if you compare with Arrhenius equation, which is K of the reaction is equal to A into e raised to power of minus EA by RT. So the only difference what we found here is this factor and this factor. So therefore, A is equal to A dash into under root of T, which means according to Arrhenius equation, see this line should be mentioned always that according to Arrhenius equation, uh, A is independent of temperature. But according to collision theory, A is not independent of temperature. A depends on temperature. Correct? That's why there will always be difference in the theoretical value and practical value. Correct? Because theoretically we assume we take the Arrhenius equation and calculate various rate constants. But practically, when you see that the temperature factor always affects that. Okay? And that's why we will need to address that here. See how we can address rate of reaction is equal to, right, uh, Z11 into e raised to power of minus EA by RT, which is a fraction, into, we need to add one more factor, which is steric factor. This is into P, which is steric factor, which is also written as Z11 into F into P. Remember this Z11 is bimolecular frequency of the bimolecular collision frequency. F is the fraction of particles which are crossing the barrier to form products. And P is the steric factor. P is the steric factor. Yeah. Steric factor is like a probability factor whose values lies between 0 to 1. Typically, theoretically, it should lie between 0 to 1. Okay. See. So here we have two things. If theoretical value, theoretical value, okay, is greater than greater than 1, uh, greater than experimental value, then to compensate that, P has to be less than 1. P has to be less than 1. Second, if theoretical result theoretical result is less than experimental result, experimental value, then P has to be greater than 1. Okay. So in 2017, the same question has been asked everybody. It is just to pick out the options. Okay. It was given theoretical value is greater than, is less than the experimental value. Then the P value is 4.5. Is it correct or not? The answer is yes. This P value has to be greater than 1 in that case. Okay. So remember in which case what will happen. Got it? Next. If you notice activation energy, activation energy is the uh, energy or minimum energy required for making the particles to reach to the highest energy point. After that, only products can be formed. Okay. So if you have to show it through the plot here, where we are writing in terms of fraction of particles, correct? So it is energy here, energy in terms of this particles, dN by N into dE. D is the energy. So in that case, I can write as two graphs here like this way. Okay. Now, if you notice that activation energy is somewhere like a kinetic energy, where this is like the minimum energy which reactants needs to have to convert into products. Now, if you compare this value here, this area, you notice this area is at a temperature T, while if you compare this entire area here, if you compare this entire area, that is at temperature T2, and T2 is T1 plus 10. Imagine if it is T1 plus 10, correct? Then how much will be this area of this shade? So then area under the curve, correct, has to be almost approximately 2 times area under the curve of T1. This is curve of T2, correct? Which means more number of fraction of particles will cross, because more the area means more number of fraction of, this is fraction only, right? So more the fraction of particles. So more the fraction of particles will cross the barrier, correct? So as the temperature increases, activation is just constant, but the number of particles which are crossing the barrier will always increase. Okay, right. Now, last thing we need to know is that suppose if a graph is given, you should be able to analyze that graph from here if it is given this way. So if this is the reactant energy, this is the product energy. What all terms we should know out of this is first, what is this one? This one is threshold energy, TE, threshold energy. Okay, or let me write down it as 1. Okay, next factor is this one, from here till here. What is this one? Sorry, it from here to here. So let this be 2. This be 2. And similarly, if you notice from here to here, almost from this point to this point here. Okay, from here to here, let this be 3. Right? And the difference between the reactant and product. Okay, and if you notice the difference here, this one is the difference. Okay, let this be 4. So one is threshold energy, and 2 is activation energy. 3 is, this is also activation energy, but this is in forward direction. This is activation energy in backward direction. Activation energy in backward direction. Fourth is, delta H of the reaction. Fourth is delta H of the reaction. Yeah. So if products are more, reactants are less energy, then delta H of reaction in this case is greater than 0. Generally, we will say delta H of reaction is always equal to activation energy forward minus activation energy back. Correct. So you will be asked to use this formula and do some calculations based on this. So either one of the factors would be missing. So based on that, you need to check, first calculate, and then suggest whether it is endothermic or exothermic and so on. Correct. So questions related to this also, one of the questions I have put it in the class notes. So I suggest you to go through that once. So I think more or less these are the areas which you need to cover, everybody. So theory wise, everything has been covered, I guess. Now, my point is you need to solve the questions which I gave you yesterday. Please solve the questions from the assignment which I've sent you. Okay. Important questions and PYQs is what we will touch tomorrow. We will discuss all the questions which are important from the assignment as well as from a few PYQs. As we finish, then we'll start, as we almost get to a completion, then I'll take some time to give you briefing on structure of atom. Okay. But today, spend enough time to solve the questions. First, read the synopsis, whatever we have discussed today, and then complete the questionnaires. Okay. If anybody has any doubts, please do ask.